you don't mind, we could do.
Sounds good.
Great. Thank you. And I'll turn it over to you guys.
Yeah, I'm hoping we can just go around the room, get some introductions, understand what the various roles are on the Beck side specifically, but I'll start. I'm Taylor LaForge. I'm the project manager on MKA's end for the museum expansion. And MKA is this structural engineer of record. So maybe the
all right, yes. So I'm Dave Devaney. I'm the project executive, team lead right now through the pre-con phase. We've got two other guys, Mike and Mark, that are from pre-con that are on spring break this week here, so they aren't able to join us. But I'm just leading the charge here for Beck today. So.
Gotcha.
I'm Clifton Ball, senior project manager for Weissman Freddie.
Yeah, the other Beck guys, do you guys want to introduce yourselves? Just tell us a little bit about what your role is. And
yeah, I can. I'm Sawyer Roussel. I'm a senior pre-construction engineer with Beck, and I think I'll actually be doing a lot of the steel for this job, a lot of the structure work. I'll do my own takeoff and things like that, but also communicating with all the subs that we're going out to bid with, kind of managing their RFIs, but also hearing what you say today, answering some of their questions that they may have going forward. So I'll be doing that, and then I can pass it to Tim Bernard.
Yeah, good morning, or I guess good afternoon. Sorry, I got a little bit of some maintenance work going on here at my place. It gets a little loud, but I'm the project manager here at Beck. One of them. I'll be helping support Sawyer and the pre-con group with any kind of structural or any kind of questions or concerns they have, or just kind of help where I can on that side of things, and going through drawings and whatnot, and see what we do.
Awesome. Okay.
One quick one. I am Sandra Cordova. I'm going to be the design manager for this project. I'm a registered architect here in Florida, and I work on Beck architecture. But for this particular project, and my role is really just going to be a liaison between pre-construction and architecture, all of the different designers. We want to make sure that every communication that we push through to you guys yields efficient results. So we want to make sure you guys have really good RFIs, good questions, good solutions, and that we can get everybody aligned. So nice to meet you all. I'm sorry, I have camera issues today for some reason, but
it's all good. Is that everyone from the Beck team on the call?
So my name is Jordan, and I just want to kind of just clarify things. When it says Beck Envision, my name is Jordan. I'm part of the Envision team, but basically mentored and overseen by the Beck group. We're dividing and conquering bid packages. I'm just here to for a learning opportunity. I'm mostly focusing on interior construction and interior finishes and managing that process, but it's really great to meet everyone here, just to make that very clear that Envision is providing staffing and supporting this project.
Okay, thanks, Jordan. Well, I think we should probably jump into the structural drawings. So my plan today is just to walk through the plan sheets, describe the structural systems, the unique elements structurally on the new building. And I would ask, don't hold your questions to the end. If anything piques your curiosity, you want to talk about in more detail, just speak up. Otherwise, I'm just going to feel like I'm speaking into the void for the next 20 minutes. So unless there are any objections, I'm just going to start sharing screen and flip through our drawing set. The Beck team, have you had a chance to look through structural drawings yet?
Briefly
Yes.
been through them, yeah.
Okay.
Been through them a little bit too.
Gotcha. So 60,000 square foot museum expansion, primary structural systems are drilled shaft foundations with isolated pile caps, concrete core wall with a mat foundation supported off of drilled shafts underneath, and a majority of the floor framing and column framing is structural steel. Not very many columns for the square footage of the building. So big transfer trusses starting at level 2 that actually reach all the way up to the roof. AESS steel, very specifically detailed feature elements, big elements. I think the truss probably warrants the most attention of anything on the project structurally as we look through this today. But one other pretty unique structural item that we don't want to, we want to give some time to, the rooftop canopy. It's with the tapered edges and the round oculus opening. With that high level description, we're going to start flipping over to plan sheets. I'd like to start with our foundation plans. So load maps, pretty normal stuff. We've also got slab edged tension plans in the set. So that lives with us rather than the architectural drawings. If anyone's looking for that at this point. Plan sheets, just like the architectural set, broken up into a west sector and an east sector. This is our level 1, slab on grade, bearing on soil, 2 different shaft diameters utilized on the project. At one point, we attempted to just have 1 shaft diameter, or we actually explored a variety of different shaft diameters, but we found we have larger diameter shafts under the most heavily loaded columns and under our core walls, and then smaller diameter shafts under the more lightly loaded columns. Let's see, core walls, two cores, west core and east core. East core is slightly irregularly shaped, where it mirrors the edge of the parking garage just adjacent to it. We're also straddling an existing pile cap, and the mat foundation actually gets poured around that pile cap, but not over it. And the core wall spans briefly over that pile cap as to not load it. And that is a pile cap supporting a column in that garage. 18-inch thick walls, fairly lightly reinforced compared to what you might see on the West Coast, which we do a lot of that stuff, but pretty typical East Coast non-seismic reinforcing in these walls. The one exception being some dense reinforcement in this side, the west side of the east core wall, which has embedded steel beam at level 2 that helps to support the truss. I will show that when we get to the level 2 framing, but by embedding a steel column in the wall, we do have some densely tied up reinforcement directly under the embedded beams to confine the concrete. Let's see, I think that covers most of the particularly, that's a good high level summary of level 1. Yeah, we primarily steel columns coming up off of our pile caps, although we do have a concrete mezzanine slab for to limit head height between level 1 and the mezzanine. There is a 10-inch thick concrete slab at this smaller intermediate level. And because of the concrete slab, and there are a handful of columns that only come up to support the mezzanine, there are a few concrete columns, very small concrete columns. You can see them here, 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 here. Everything else, steel columns. Mezzanine level, we do have some raked.
Hey, one question on that slab, is it supported by steel? I mean, it's a structural
It's
steel.
partially supported by steel, where out we have steel columns that need to continue up to support level 2 and above. So what we do, there is steel framing that will need to be in place to support the concrete slab. For instance, this column here tracks up and supports truss up above. So we have, it needs to be steel at this level, and we have beams running from steel column to steel column for the concrete slab to be supported off of.
Okay, so in this area, it's not supported on metal deck. It's actually supported by concrete.
It's concrete
roof
flat
or
slab.
Flat
Yeah.
slab, sure. Okay.
That's right. So there are a few regions of concrete on metal deck at the mezzanine. This zone here, these wings on either side of the auditorium are slab on metal deck because the spans allow it. But in this zone where you're not seeing infilling steel beams, that's all 10-inch thick concrete flat slab. Auditorium,
Mild reinforced, no PT.
no PT. That's correct. Yeah, mild reinforced. Good question. Yeah, no PT on the job. Raked raker beams supporting concrete on metal deck, seating risers, treads and risers for the auditorium seating. Lots of details to cover that. The feature stair also goes from level 1 up here, landing at mezzanine level, and continues to track up. It's not all that elaborate structurally. It's straight runs of steel framing, all wide flange frames, no giant welded up tubes that you might get with like a coiling feature stair. See, we do have some AESS designations on exposed columns in this area down here. These tube columns are designated AESS. I'm going to go back to level 1. And generally, we have indicated what elements are required to be AESS with notes on plans. And those have been tracked and coordinated with the language in the AESS spec, which tells you exactly what level AESS members are held to and defines the levels of AESS. I bring that up because a large portion of those trusses at level 2 are AESS, and that is something you guys are certainly going to want to be looking at in detail. So I'm gonna fly past. These are the mat foundations under our core walls. They mild reinforcement. We do require vertical reinforcement in the mat foundation, all over the entire footprint of the west mat and a portion of the east mat. Let's see. Happen upon that. I'm just going to keep tracking up the building. I think we've covered the mezzanine well. I'm going to move to level 2. This is a reinforcing plan for the mezzanine, mild reinforcing. Level 2. Level 2, a bulk of the perimeter of the main floor plate is truss. So I'm going to highlight those trusses now. Truss, truss on the east side. Truss continues all along the south, wraps the corner here, tracks back. And there is a zone that doesn't have truss on the north side, where the trusses just weren't, trussing was not necessary. I am going to flip over to our truss elevations just to show sizes and extents. Let's see.
Taylor, one thing to step in, can you go back to the plan that you were just at?
Absolutely.
So you were briefly discussing about the idea of AESS and the requirements of the truss. So from our standpoint, please correct me if I'm wrong, Taylor, but like, you know, some of these trusses are enclosed or within out of view conditions. So the expectation is that it's the ASS is relevant to the exposed truss portions and not the back of house ones.
Yeah, and specifically where, and that's worth me giving a little more clarification. The exposed trusses are primarily out here, I believe exclusively out here in the event space. Back, the trusses over on the east portion of the building are all concealed and not considered no AESS requirement. And further, the green highlights the event space trusses. The entirety of the truss is not exposed. It's only the verticals and diagonals. The chord elements are not exposed. Verticals and diagonals and the connections between the verticals and the diagonals. The verticals connect to the chords and those connections are concealed. So it's only a portion of the event space truss that is actually exposed. And I'm going to hop back over to the truss elevations. That has been explicitly noted on the truss elevation. So this elevation here, this bottom elevation, we're looking at the south side of the building, looking towards the north. The river's over here. Nice 60-foot cantilever off the nearest column at the far west side. And we zoom in on our member sizes. W14s, size, the weights range dramatically from fairly light, like 159 pound per foot, all the way up to some really hefty, on this side, 665s, but we actually have some even heavier members on the north side. But variation in member size, and we've noted which of these require AESS prep and finishing. Notice the chord elements, the W36 chords, no AESS requirement. As we track further along, for instance, on this particular column is AESS above level 2 because it is not, that column is not exposed below level 2. So we try to be very explicit about what elements require AESS and what elements do not. And what I was saying before about connections, the diagonals, where the truss is exposed, the diagonals come in and intersect the truss verticals away from the truss cord. And we'll look at it, the detail for that, because it's a unique element of the project. Where the diagonal intersects the vertical, that is exposed to view and needs to be treated very carefully. But where the vertical comes down and actually intersects the W36, that occurs in the slab and is not exposed. So that does not need the same AESS treatment. So it's really a subset of the truss elements and a subset of the truss connections that require the AESS prep. And then once we move past grid line 9 on the south side, and we're moving into, there's some backup house stuff on the second floor mezzanine. This is a mechanical well. All this truss is concealed. No AESS, and another important designation for the steel team, we go from engineer of record designed steel connections at the exposed truss to your more typical fabricator design, steel detailer design, steel connections in the back of house, where we are not sensitive to the appearance of the connections. And these these tags, these D32, D33 tags, those track back to a schedule that gives the detailer all the forces that they will need to detail that connection.
With that, excuse me, sorry to interrupt.
No, it's
With that being said, some of your details are calling out like delegated design and stuff. Is that what you mean by that? It's kind of, you're kind of putting in the fabricator or installer's port.
That's correct.
Okay.
Yeah, more, I would call that like East Coast style connection design.
All right.
That's how we refer to it. On the
Okay.
seismic world, we end up detailing all the connections, but yeah, this is delegated connection design. You could also call that like the steel detailer connection design.
Okay. Okay. Good enough. Thanks.
The other thing to note, from this particular truss at at column line 9 has a rated partition that it has to support. So this truss and Taylor's designated FP2 across these members. So, and this is an area where the fire protection, our building is a 1-hour rating, but in this area, this truss area, it requires a 2-hour rating.
Okay, that's good to know.
Yeah, it's a great point, David. We've been very explicit about what members require the 2-hour fire rating.
Yeah, that'd be good for costs and stuff and application for sure.
Right.
And as it relates to fireproofing, so intertumescent paint versus spray on fireproofing, is that
For the exposed elements, yes.
But in the back of house, unexposed, David, we're expecting spray, right?
That's right.
For comparison, we'll look at the north side truss. Because of the angle of the far west side of the event space, it starts to jut out as on the north tip of the event space. We've got a longer cantilever on the north side. Instead of 60 feet, it's 90 feet. And that means we just have some very, very large members at that leading column. And the foundations are also large to resolve the big forces. So this is the biggest, heaviest member on the project. These two elements here, the 14 by 808s column and diagonal. And this connection is very robust, where those two heavy elements come together. And like I was saying before, this truss, it stops here, no truss for a few bays, and then match line, and here's the other side of the match line. Just because this truss is a little bit longer, it doesn't fit all the way on the sheet. Some shallower trussing supporting the mechanical well space at the second floor mezzanine. Let's see. One thing a sharp eye might notice: what's supporting the truss on this end? Is it really cantilevering off of grid line 9? Not exactly. I'm going to go back to the second floor plan. I was alluding to this before, but this is level 2. This is the east core, and we're looking at the ends of those shallower trusses here. This W40 is embedded in the 18-inch thick core wall, and actually cantilevers out of the core to pick up the end of the truss. So unique support condition here. That same support condition also happens at the second floor mezzanine. We have two at the top and bottom core of the truss. We have W40s reaching out of the core wall to pick up that framing, the truss framing.
So to be clear there, those are embedded in the concrete shear wall, those
correct. Yeah, we've sized them to be narrow enough to allow the steel reinforcing in the core wall to run past, but it is a really critical sequencing consideration that the shear wall needs to be there with this beam embedded in it to support the trusses. at least in their final condition.
I had a quick question regarding the connections. This is
Yeah.
Alejandro. I'm with the virtual construct coordination team.
Yeah.
Just for us to consider gusset plates and connection plates during BIM coordination and construction. Are there any restrictions on the visible side of it, on the open space, the public space for the gusset plates sizes? And then on the areas that it's back of house space, are there any specific requirements for that?
The connections in the exposed in the event space are all direct weld connections. There are no gussets. And those connections have been detailed by the design team. So there's no delegated connection designed for the trusses out in the green highlight area. In the back of house, delegated connection design zone, we expect there will be gussets, bolts. And as far as restrictions to the size of the gussets, I don't know of anything offhand. I imagine that will be part of the detailed clash detection exercises that go on the contractor end to make sure there's no conduit or pipe trying to route through a space that ends up getting occupied by a gusset. That's the only thing I can think of off the top of my head. Gusset wise, I think that's a very general question, Alejandro, but I hope I've answered at least part of it. There's no gussets in the exposed area.
Yeah, that helps. Just that way we can understand what we need to consider before we get the steel subcontractor on board and they start
Right.
detailing all their gusset plates.
Right. Other unique elements on level 2, we have a requirement for some supplemental damping. There are proprietary systems that can be there's a proprietary system that needs to be installed under the level 2 event space to add damping to the floor to limit vibration because of the long spanning floor beams. It's more to do with the long spanning floor beams than it is to do with the fact that we have these big trusses. The trusses are actually quite a bit stiffer than the built up floor beams. And I guess, yeah, on that same subject, we have built up girders achieving the long span between trusses in the north-south direction, both at level 2 and at the roof. There's exterior deck at level 2 in this sculpture terrace. It's depressed. It's got sloped top of concrete to drain. Plenty of details for that, primarily in architectural drawings. Hanging from the framing, below the framing at level 2, strong points. We have details for those. They're pretty interesting, like double tube strong point supports that provide support for like a retractable. David, I forget what we're calling it, but it's a combo strong point and electrical outlet for flexibility and rigging below. So those strong points are indicated by some of these annotation. I actually forget. We have 2 different annotations here.
Yeah, that's right. So they're called bus ports. We talked about them during the TLC call. And I alluded to the fact that it's that they retract and their cables go in a certain direction, but there's so the orientation of them is quite important because like Taylor and our team have coordinated the steel direction so that those tubes that support the bus ports are all in line with the primary steel so that you're not adding a bunch of miscellaneous steel members to accommodate them where possible.
Yeah, these have been coordinated to a T. Those round target symbols are the strong points. Then we also have sculpture tie downs that are fastened to the top of the beams out in this area too.
What's the fireproofing in that area then? Is that spray fireproofing?
It would be spray. I would expect it to be spray. I don't know why it would be anything else.
Yeah, it's concealed to view. It would be spray. So
I think that covers the unique elements of level 2. I will say we have long deck edges, so we frequently have steel reinforcing for the deck edges, more than just bent metal plate. There are oftentimes channels cantilevering out to help support those deck edges. Pretty consistently at level 2, 3, and 4, we have long deck edges. So that's something that could easily be missed as Sawyer, you're doing a takeoff. So pay close attention to those details. I'm gonna track up to not level 3, level 2 mezzanine. Smaller floor plate than level 2 to give that double heights, get that double height space out in the event space and this hallway here. Big mechanical well at level 2 mezzanine. It's got a dunnage platform that we've detailed, round HSS tubes with a grillage of wide flange framing above. Nothing too unique there. Once again, we have W40 embedded in the west face of the east core to help support the trusses on the north and south side of the building. Don't think there's really anything else exciting to talk about this. Level 4, the roof, occupied roof. I guess it's not fully. There's also a high roof over interior space around the east core. There are a bunch of 8 inch or 8 5/8 inch diameter tube columns that start on this level to support the canopy up above. We also have a built-up slab plinth for sculpture support, and that plinth mirrors the shape of the opening in the roof above, or it's at least round, like the opening in the roof above. We have sculpture tie downs that get embedded in the concrete. Like I was saying before, there are some extended deck edges. We have specific details for those. The level 2 exposed trusses are coming all the way up from this level. So this is the top of the exposed trusses. And then there's a big break in the floor slab from the west core over to the east core. That big opening is the mechanical well. And over here, we just got roof, roof deck, I believe, not composite deck, over the lid of this space. And now I'm going to flip over to the canopy roof, the high roof plan. Structure here is a little unique. At its most basic level, we have a large HSS tube, a 16 by 16 tube that follows the perimeter of the tapered canopy, and that's at the ridge line, the tapered canopy. And off of that, we have steel, specially fabricated steel channels, I shouldn't say, just fabricated steel channels that taper down to support metal deck spanning between those to form this tapered canopy edge. And it's a torsion tube, 16 by 16 torsion tube with finger elements made of steel channels coming off of it at regular spacing. And then we have a similar condition for the oculus, which also has tapering roof profile with just a smaller scale version of those same channels that we have around the perimeter. Lots of details here, details to cover the unique corner conditions, details to cover the various connections. This is all delegated connection design, so we're reporting lots of loads for the connection detailer to use to detail those connections. And we are looking at roof deck up here. This is not composite deck down below. It's composite deck. This is just roof deck. Any questions on this before we start getting into details? I think I'll show some sections just to reinforce what this roof canopy looks like. So we're gonna go 515.
Yeah, I'd love to see like tapering those members like you were just talking about,
Yeah.
something about that. Yeah.
This is the typical detail. So 16 by 16 tube, channel coming off, cut on a slope, and a 6x4 angle welded back to it to form that slope. And as we get to kind of the knife's edge, that 6x4 angle stops, and we have a bent plate that runs along the perimeter coming down to this structural tip.
To get that
Everything
point,
off of
yeah.
that is just built up.
So the member isn't necessarily tapered, it's just the profile of the overall construction.
Right,
Mhm.
right.
Is that then structural steel framing? I said like gauge, but engineer delegated engineering stud framing to create that roof pocket there
Yeah,
on the backside of that bent plate and the underside of that.
right. The build up here, it's really well supported. This bent plate is continuous, so
Oh, wow.
it's not like you
Okay.
need stud framing to do any work there.
Okay.
I don't know off the top of my head what gets applied to the top of our roof deck or what's going on down here. I think David, we probably have stud framing to soften this, right?
That's right. So
Yeah.
the metal panel detailing in the architectural set indicates the backup framing or
Yeah, just to build out the soffit, but then metal framing, metal panel stuff sitting on top. Okay, I don't see a lot of value in going through all of our typical details. I think we're just going to look at some very specific details. And I want to start with the trusses. So going back to our truss elevations, I guess before I do this, I did skip over one element of the lateral force resisting system. Let's go back to the 3D. I was saying before our, go to the axon views, actually, it's a little easier to see. Our primary lateral force resisting elements, we have core, that's our west core. We're looking at the project from the northwest. East core, and you'll notice what I'm calling a west core, really not even remotely close to the west edge of the building. So what we have two supplementary braced frames as far to the west as we can get them. So these two frames at grid line, I think 4 and 5, if I'm remembering off the top of my head, but those two frames, they have twins on the south side of the building. So north side, there's 2 frames, brace frames. On the south side, there are 2 frames as well. I'd be remiss if I didn't mention those. Okay, so back to what I was getting at with the steel truss connections. So in the exposed zone, we call out at each connection a detail. So most typical diagonal to vertical connection, 28 on S321. We have W14 diagonal intersecting W14 vertical. There's a full CJP weld between the diagonal and the vertical, reinforcing flange plates or flange continuity plates that turn the corner, run horizontal where the diagonal is coming into the vertical. Occasionally, we are also requiring that the web of the vertical get doubled, gets a reinforcing plate to add heft to that connection. You can imagine this, basically what I've highlighted in blue here is a node. This node is doing a lot of work. It's reinforced. And then that reinforced section of the vertical comes down and gets welded to the truss cord, bottom cord, same condition at the top. It's just flipped around. And once again, there are some vertical plates that continue the flange of the vertical element down through the depth of the truss cord. And also we require, in some cases, a web doubler plate on the truss cord. So very detailed connection. These connections, these are the exposed connections. These are all fully detailed in our drawings. That's the typical condition at the exposed truss. At the back of house condition, let's see. We have indicative details to cover the back of house trusses, where we give general information and criteria for the delegated connection designer to utilize. And we've shown indicatively gussets, like Alejandro was asking about. I expect there will probably be gussets, but this is ultimately the details of the connection are left to the connection detailer. We'll review the concepts through the submittal process. Other details worth going through. There's some sections through our mat foundations. We should probably spend a minute looking at the typical drilled shaft details. So the drilled shafts, the geotechnical report gives a lot of information about means and methods of constructing the drilled shafts, including requirements for pilot holes being bored at drilled shaft locations, geotechnical requirements for observing the hole prior to casting the drilled shafts. We've given, for every single drilled shaft, we've scheduled every drilled shaft with the specific reinforcing required, the estimated required bedrock embedment based on the geotechnical information, and also to supplement that, how much load we are resisting at that drilled shaft, which the geotechnical engineer would use if needed to adjust the bedrock embedment in the field based on actual conditions. And what you'll see are the diameters are either 5 foot or 3 foot diameter, depending on load. The really big loads, particularly under the truss columns and under the core walls, require the 5 foot diameter shafts.
Have pilot holes been done under each drilled shaft, or just a couple?
I don't believe so. I don't believe so. I think that is a
pilot holes have not been done.
Okay. And who's the geotech for this?
Terracon.
And while I got you on this conversation, Zach, can we see I don't think we've seen the look at the specs. I don't see a geotech report.
Yeah, we can share the geotech.
Right. But I'm guessing on some of those bigger ones, it'd be good to get a pilot hole done. I don't know, maybe before we get a drilled shaft guy on board.
Yeah, we can have that discussion.
Yeah, I could see there being some value locating top of rock and evaluating the quality of the rock at those specific locations. Other good details to review. I think the other thing I was wanting to share let's look. Here's feature stair sections. So like I was saying before, straight runs of stair, it's not all that complicated. We do have some hanging support at midpoint of the upper run of stair. But we don't have any twists and turns in the stair that the stringers are having to accommodate. So it's all wide flange framing. I think that is the end of what I plan to show from the drawings. So now I would open the floor up to questions from Beck or any other points that Weissman Freddie wants to make that they thought about while I was talking.
Yeah, I can start the conversation. It looks like you've got the ASS spec open.
I do.
So in our spec, the way we looked at it was, I guess you can say like there's two ASS qualities that we identified, a 4 and a custom. And the custom one, we basically, have these vertical round columns that exist on the project on the ground floor, supporting the terrace above it. And then also on the 4th floor, these round tubes. And basically we just needed to create like a simple custom ASS, which is saying like, we're worried that you're going to have clean surfaces to prep for, paint. And so we tried to identify the round ones as like kind of a custom, where it's not really about the connections, because all the connections happen above and below the view. So it's really just about the outside surface of the and the tolerance of the steel for you.
So we define here in the summary that the following structural steel elements and connections need to fall under ASS 4 category, and that would be the exposed portion of the trusses and brace frames. The following elements need to follow the custom, the C1 ASS category. Those are the ground columns, the ground floor, and the fourth floor event space, and the fourth floor terrace, like David was just describing. David, this is obsolete, right? The dog park canopy.
Yeah, that's out. Well, that will come back in another form, but not right now. Yeah. So maybe you can go to the bottom chart on the last page. So essentially, this is the ASS requirements that are typical, right? So for ASS custom, like you can see, we're focused on that there's not any markings that are happening on the pipes or the tubes themselves. So it's, that's kind of the limit of our ASS requirement for that. For the ASS 4, what we're mainly worried about is like when they cut, like, it's going to come in pieces. So when they have these long truss cords, like that they're cut from the same extrusion, so that when they line up with each other, you don't have any offsets occurring from one member to the other. Am I describing that right, Taylor?
Yeah, I mean, that's among other things. It's also the quality of the welding.
That's right.
Particularly these connections, let's go back to that sheet. 321. These connections are going to be experienced by people in the event space. Like, this is right at your knee. They're going to be touching these. These are feature elements. So ASS 4 basically covers that condition, an element that patrons or people in the space are able to touch. It's alignment, it's quality of welding, it's removal of any erection aids, because I'm certain there'll be some erection aids at some location along these members, and cleaning all that up. And I think an important acknowledgement with the ASS 4 on the steel trusses is they will have a high quality intumescent paint layer on them. I think acknowledging that will conceal certain, that may be able to conceal some very minor defects, but the final product needs to look ASS 4 quality. right. Any other hot points in your mind, David?
No, I think you did a great job describing the project. Thanks for going through that, Kendall.
For sure. How about that, guys?
I got a question with that detail right there. Why do not the stiffener plates go all the way down to the web?
Why do they go all the way down to the web? Or why
Why
don't
do
they go?
why do they not? Right right there.
They just don't need to. What happens is there's because of the eccentricities in this connection, the diagonal is pushing on the vertical, and there is a big moment at the connection between the vertical and the chord below. And so those continuity plates, those flange continuity plates come down. It's a deep beam. It's a W36. They come down. They have load in them where they first start, and they start to shed load into the web. And they have enough length, that L1 length, which is variable. We have just enough L1 length to shed all that load into the web of the truss cord. I mean, if for some reason you guys wanted that plate to run all the way down to the bottom flange, we wouldn't take any exception. But generally, the fabricators have a harder time doing a full depth stiffener than a partial depth.
Yeah, I think as long as it just, as far as how far we go down as identified, I think it's fine.
Yeah, gotcha. And let's look at L1. So L1, it's generally 32 on a 30 W36. So it's coming almost all the way down to the probably coming to the toe, or just the start of the radius in the web, between the web and the flange at the bottom of the beam.
Okay, makes sense. I was kind of curious when I saw that detail the other day. So
sure,
cool.
Yeah.
Thanks.
Mm-hmm.
I got a couple. So can we go to that? I guess it's the elevation drawing showing.
Yeah.
That one. So the shoring, is that something you guys have engineered, or what's the?
No, the shoring. I mean, as engineer of record, our scope stops at the final condition. We have not engineered the shoring. We don't have a means and methods like erection sequence dictated in our drawings. I expect that to be something that we talk about collectively as we get closer to building this thing.
Okay, because that was the other erection sequence. I've done a couple of complicated, and they had a specific like 1, 2, 3 erection sequence. So you guys haven't established a set.
No, we don't have
this has got to be
requirements for the erection sequence, other than this thing needs to stay stable while it's being built. Once you have the roof and the level 2 diaphragms poured, it's all locked in. But before then, the stability of the truss is kind of its own beast. And this project's going to need a capable erection engineer.
Right.
Yeah. So Dave, on our side, we just try to get like a work packet or something like that for our installer. Basically what you're saying is calling them piece marks and stuff, just for, obviously laydown area is going to be limited and all that stuff. So it's definitely a lot to think about.
Yeah, I just wondered, now going back to the floor plan, I guess from your side, because there's a couple schools of thought on, we had presented a tower crane, but looking at a plan, there's enough room between that shear wall and that northwest corner of the building to crawl a crawler in there. But to do that, you'd only have, you'd have to crawl your way out before because there's no way to crawl this crawler to the south. It's got to go out to the north. So is there like not a poor sequence, but is there, from a structural standpoint, could you pour through to column? Is that column? No, you couldn't get a 9. Could you pour to 7 or something like that? A pour break, and would that support the structure? You follow what I'm saying?
I think we got to think about the truss continuity if we're going to do any leave outs, because the south truss does continue across the entire width of the building. So you're talking about leaving out a portion of that. Is it feasible? probably. Is it part of the base design? No.
And then these trusses, this is a relatively new thing for me. Do they, I mean, I'm guessing they typically erect them like in segments and, I mean, assemble them in segments on the ground and fly them up in segments.
I would absolutely expect that. We had some conversations with fabricators early on, kind of mid-design, and we're trying to understand what they might do as far as breaking them up. They're so tall. They're 36 feet tall. One of the options that was being discussed, they would be fabricated in as long of segments as possible and spliced potentially at the midpoint. You take two pieces and bring them together in the field. Other options would be long cord pieces with splices just off the nodes. And then, so let me draw this. Like this may be a piece. This may be a piece. And then infill, these are infill chunks, but that's more field welding to put those together. So those are all welded connections to look continuous in the final condition. So I would expect as much shop fabrication as possible. The elements brought out the site, assembled on the ground to bigger chunks, about as big as the crane can handle, erected and then locked into place in the air. You're going to want to minimize the amount of connection that you're doing in the air.
Yeah, we could build them like in some like little small modules or something like that, and put them in big, like I said, big chunks. Easy. I don't know how much room. That's something we'll just have to look at. How much room we got over there.
Yeah, where you're actually able to lay down and put things.
And the weight. That's where I get where like the tower crane. We want a tower crane. It's like the limitations and the weight. It's probably pretty heavy. Some of those.
Right.
Oh yeah.
Some sections.
Yeah, particularly over here.
Okay, what else on that?
I don't. I think we definitely have a lot of coordination to do as we move forward on getting this in place for sure. The one I do, can we just look at that detail of the beam embedded into the shear wall?
Yeah, it's going to take me a second to find the detail in the set, but we'll start with the plan. Second floor framing plan.
And I got a question while we're sitting here before we get to that. So here, have you taken into consideration the garage? I'm just trying to think of the formwork for the shear wall, and they'll want to slide it up. What kind of distance do we have between that shear wall and the face of the existing garage? Do we know? Is there any room to slide the formwork up?
Yeah, it's close, right?
Well, there's a finish on
the metal panel finish, right?
Yeah, right. So there's some dimension.
But that's, I mean, if that forming system's, Tim, you know how big that there's, and that's, I'm thinking the metal panel system is 6 or 8 inches thick, but that formwork is a lot thicker than that.
Yeah.
I'd have to look at the Revit model, but I don't have the existing loaded in. But
I can't remember, David, are we removing we're obviously moving the precast from the garage right there, or just actually we're just cutting where the door goes, right? At each of those.
Just small cutouts. But if you give me a second, I'll pull up the architectural details and we can talk about it. But
okay.
Taylor, if you want to pull up the embedded beam while I do that.
Yeah. So it's the W40 by 294 in the 18-inch thick wall. I believe this is our detail 100306. Yeah, here you go. So it's tight. That W40 is in the wall. The verts, the wall reinforcement run past, and then we have some strap plate, some through bolts through the wide flange and some strap plates running along to mimic the ties you typically would have in the wall to tie up the concrete. We don't usually have ties in our shield wall except around this embedded column because of the load it's putting in. We're confining the column, or I'm sorry, we're confining the wall around that embedded beam only for the first 4.5 feet. There's dense reinforcing in the wall for the first 4.5 feet of that beam being embedded. But this is the detail you're looking for, Tim.
Okay, yeah, I was looking at the other day. I thought that's what you guys were trying to do. And I'm like, oh no, surely not.
Yeah, no, it's a special detail.
Yeah, that'll be good. That'll be fun.
Yeah, agreed.
Do we
And
have
how does
a,
it- Go ahead.
sir, do we have a detail for the corner where the two walls join by any chance?
A specific detail for where this is coming out of the wall.
No, if you can go back to the floor plan,
Yeah.
the north corner and the south corner.
You're talking about here and here, right?
Correct.
Yeah, I mean, that detail that we were just looking at, it is telling you what that section is going to look like. I mean, it's no different at the corner than it is right off the corner. But what I will show you are our shear wall sections. So here you go. This is just below the embedded beam. We're actually showing the embedded beam in the dashed line, but this is what I'm talking about tied up reinforcement around that, which is more dense reinforcement. It's still honestly not that tight compared to what you'd get on the West Coast. 3's at 12. This would be 3's at 3, 3's at 4 in seismic country. But there is some denser reinforcing to confine the concrete right below those embedded beams. Basically, that confined reinforcement goes up to the underside of the level 2 mezzanine, where you have the higher of the two embedded beams. Are you looking for something else, Alejandro?
Yeah, probably exactly at the location where the beam is at. May I share my screen really quick?
You can, yes.
You know, you can see my Navisworks model.
Yes.
So this is that corner, looking at this wall and the wall on the other side. Just the rebar that is tying into the corner at this elevation where we have the beam. That's really what I was looking for.
Oh, I see. Yeah, it's similar to the detail that I was sharing that showed the through bolts. The through bolts would still be there at the corner. I think the one thing you're probably looking for is how does the horizontal reinforcement in that wall terminate?
Right.
And what it's going to do is it's going to hook. All that bar is going to hook before it gets interrupted by the beam. So through the depth of the beam, this reinforcement here is going to hook. It's going to stop at the beam. It's going to hook, and over here, that wall, that reinforcement probably needs to have 180-degree hooks through the depth of the W40 beam, so it doesn't end up clashing with the W40. I think that's a fair question. That specific level of detail, I don't think we have covered in any of our details, but
would it be of benefit if we model the rebar just at this location? I'd like to show you an example of what we did on another job that helped us a little just to understand the rebar at these locations specifically, especially when we start having a lot of stirrups and
Sure.
embeds at the corners, and then with the concrete mix.
I have to guess that this project doesn't have many conditions that would warrant 3D modeling of rebar, but if anything does, it would be around these embedded columns or these embedded beams. This is the embedded beams in the east core and possibly the condition in the pile, sorry, the pile cap at the base of the east core where we are notching to avoid the existing pile cap, that's another congested area. Other than that, our reinforcing is not very complex. And I don't think would warrant 3D modeling, but yeah, I could see there certainly being a benefit to modeling this particular area.
That specific section. Okay. And then I think, Dave, you had a question here between the existing wall of the parking garage and our new building. I'm getting about 6 inches between that panel and
Is that to the shear wall or is to the finish wall? It
that is
sounds like
to
finish
the
wall.
finish wall, correct?
Here,
Maybe yours to the-
I can
to
take
the
I'll take the presentation for a second and give it back to you.
And I think about that from again, we're getting way into the weeds, but even if it's finished panels, how do you caulk those panels? And that's gonna
So based on the site survey, we had them survey kind of the edge of the building and the edge of the garage. So the garage has this, I forget it's exactly, it's a 7-inch precast edge here, or 6-inch. But we expect the face of our building's center line of the 18-inch wall to be 2'8" from the face of their precast panel. So, you know, what we're talking about is basically 1'11" from the face of concrete to the face of precast. These panels are a hook and pin, so they're not sealed. Your waterproofing layer is at the sheathing, and yeah, you're sealing the penetrations and hanging the panels off of the system. There's a plate that's intended to capture the transition, so it can so the two can slip past each other. There is, just to add, there's, you can kind of see it. This is a unique quality of the garage, but we drew it. So this is the column below that Taylor's referring to. What the ground floor has, the footing that's got to be, the cap that's got to be maneuvered around, and then up at the upper levels, the column reduces in size, although it stays pretty close to the precast as it goes up.
Interesting.
So
Okay.
this is sheet A342. If you want to
Okay.
go back to it.
Yeah, I think the challenge will be that waterproofing, applying the waterproofing in a whatever it ends up being, 8-inch gap, 12-inch gap behind those precast panels. Okay. I think that's all I got. This is a great presentation. Thank you, Taylor.
Yeah, no, happy to talk about the project. It's been a little while.
I had a quick question, Taylor, regarding the underground utilities. Was there a lot of coordination with your foundations on that? Just trying to understand where
Yeah.
we're going to take it from.
The existing utilities, you mean?
Yeah, the existing utilities.
Yeah, I don't think we had a lot of conversation about that. I don't recall having that discussion.
Yeah, we've so being in this kind of corner of right up against the CSX rail line, the water lines, the primary lines go down Gasparilla Drive, but there is a water loop that's interrupted. Civil details that, you know, it's not going under the building, so all of our services are outside the building footprint, and primarily where this kind of east core lands, this all falls in a zone that is that's only impact would be the chiller well lines that come back to the renovation building or the existing building. So really it's this lifeline between the chiller well that exists right now. Now, with that being said, you know, where we understand those lines, we don't believe that they fall underneath that east section, but you know, with excavation and everything, they could be impacted.
Great, thank you, David. Well, maybe Dave, I'm not sure if we've received those files, the AutoCAD files from the civil team. but we can easily overlay those AutoCAD files with the foundation just to see where they're landing.
I'll get them for you. Well, that might have been an oversight on my part, but not intentional.
I appreciate it, David. You also mentioned that there was a survey done for the existing conditions, the existing building. Do you know if that was a scan? And is that something you could share with us?
Yeah, we have a survey, but it was not a scan of the underground utilities in that area. That was from, when we did the renovation, a lot of the same players were involved. So Stantec did the original work. So a lot of their background was the same, and Skanska was obviously the CM for that project. So a lot of the information was from their as-built and from their field.
Got it. So then the survey was for underground utilities, but did you mention, maybe I got this wrong, a survey for the existing building, the parking garage?
That was done by the owner's survey team. Yeah.
Okay, so maybe we could request that from them.
We have that survey as well, and we can provide that.
Great, that would be very useful. Appreciate it.
Yeah.
So I'll reach out to Civil today, and I'll package all that up into one email for you, hopefully today or tomorrow.
Thank you, David.
Any other questions from the back game? Tim, Sawyer, Brody, Sandra?
All good on my end.
I'm
All
good.
good over
Thank
here
you.
too.
Awesome. Well, thank you very much, everybody. Appreciate the time, and guess we got maybe one more of these on envelope, right?
Yeah.
Cool. Look forward to that. So,
Great to meet you guys.
Thanks.
yeah, nice to meet you. Look forward to
Thanks a lot.
Exactly.
Thank you.
Yeah.
Nice to meet you.
Thank
Thanks,
you.
Taylor.
Thanks.